Polymorphism just means many shapes in Greek. We've already seen one kind of polymorphism, which is subtype polymorphism. That is, an animal might be a bird or a cat. In this lecture, we're going to talk about another kind of polymorphism, which is parametric polymorphism, which says, well, I may have a box full of birds or a box full of cats. When we think of a box full of something in a programming language, we think of a container object. One simple kind of container is a linked list, and here's the expression of a linked list in C, where my nodes have, of course, a next pointer, and they have some kind of data. In this case, the data is a pointer to an integer. There's an asymmetry between the two types in the node class. The fact that next is a pointer to a node is absolutely crucial for the functioning of this class, because I'm going to move through the list using that next pointer. The fact that the item returned at the end of this list happens to be an integer pointer is completely incidental to the function of the list. If I wanted to have a list of floating point numbers, do I need to copy all this code and just change the word int to float everywhere? Well, that kind of thing is a maintenance nightmare. Instead, in C, what you do is use the top type, the most abstract type in C, which is called void star. Void star gets around this problem by allowing you to simply store the size of a pointer and to convert from any pointer type to any other pointer type. This is great from a maintainability point of view, but it does make the client code a little trickier in the sense that type checking doesn't really work for us anymore. Here's a simple example where I allocate an integer and initialize it to about 2 billion, then allocate a node and initialize it to point to that integer. Note that this is just a single element list. And so if I get the last element, I will get out the thing that I just put in. So it'll get out P. So here I have Q as an alias for P. They'll point to exactly the same location in memory. And yet look at their types. Q is a pointer to a double. P is a pointer to an integer. I'm going to get in trouble here. In fact, I have unsafe access on line 13, and depending upon the compiler, I might get total rubbish. This program has undefined behavior in C, as we saw in our lecture on safety. And this is really sad. Why is this happening? It's happening because the return type of getLast is void star, and that can be converted to anything in the C compiler. It's not a checked cast, and therefore I get the unsafe access. What happens in Java? Well, of course, I can have monomorphic lists in Java, just the way I can have monomorphic lists in C. And here I have a pointer to an integer in memory. And just like in C, I also have a most abstract type. In Java, it's called object. And this is now a generic list class, just like my void star class in C. And I can use it much the same way. Here's the same code we had for C, but translated to Java. I'm going to create an integer object and initialize it to about 2 million. I'm going to create a node and initialize it to point to that integer object. Then I'm going to attempt to get the last element of my single element list, which should give me back the thing that I put in. So I expect Q and P to be aliased. And finally, I'll try to print out Q. And note that here Q has the wrong type. Instead of looking for an integer, I'm looking for Q to be a double. Now this program will compile just fine in Java because my nodes have type object. So getLast is returning an object, and this is just a downcast from object to double, which is allowed by the language. However, unlike C, this cast is checked, and therefore I'll get a runtime error, which will tell me that, in fact, what I'm trying to look at as a double is really an integer, and therefore you can't access it as a double. Now that's an improvement over what we had in C. At least I replaced the unsafe access with an exception, and that is actually better. But it's not what I really want. What I really want is for a compiler to catch this before I even run the program. And I can do that if I use parametric polymorphism instead of subtype polymorphism. The way I'll do that is by saying that nodes are parameterized by a type X. And now I'll say that the item in a given node is going to have x. But further, all of the nodes that remain in this list will have the same type. And that means if I start off with a node at x at the beginning, and I go through all of the nodes until I get to the last one, well, the one at the end will have the same type as the one at the beginning, and I can safely return that at type x, whatever that is. Note that this method is generic. So for any x, I can take a node of type x and return x as a result. The syntax is slightly more awkward than it is in Scala because in C, the return type of a method precedes the method parameters. And the type parameter can't go there because I might need to return the result of that type. And therefore, we end up with this weird thing where the type parameter is completely separate from the value parameter. Nonetheless, it works. And if I type in the same example again, I get an error in a different place. Here, I have to specify that my node is going to be an integer node. Therefore, I expect all the data linked from there to be integers. And when I invoke getLast, the compiler knows that looking at the last element of this XS, which is a node of integers, must give me back an integer. And therefore, it can't be a double. And the compiler will reject this program before I even start to run. Now, this is a much better situation than what we had with C, where I was getting unsafe access, or what I was getting with subtype polymorphism in Java, where I was getting runtime error. Now I have a compiler error, which really is probably the best I can expect in this kind of circumstance. Parametric polymorphism is extremely successful. It's found in almost all statically typed languages. It was put into Java relatively late, in 2005, after the language had 10 years of history and had been hugely popular with an enormous amount of legacy code. And therefore, the way it's done in Java is not quite perfect. In particular, the parameter types are not stored at runtime in Java. This was done to maintain compatibility with that 10 years of Java legacy code that had already built up by 2005. In any case, the effect of it can be seen if you try and create an ArrayList class with a type parameter x that's holding some array of data. When you go to create the array initially, you'll find that Java objects to the idea of creating an array of x for some x. And why is that? It's because Java doesn't actually know the type of x at runtime, so it doesn't know what type to assign this array. The error message you get is generic array creation, not allowed. So what do you have to do? Well, you have to erase this type yourself. You put an object array there, and then to get it to store into your field, you need to do a cast. Now, this will compile, but it's going to give you a warning, and to see the warning details, you have to add a compiler option. What it's going to say here is that you have an unchecked cast. In particular, we're taking an array of objects and trying to treat that as an array of x, where x is not something that's known at runtime. Again, we don't carry these parameters around at runtime, so the runtime doesn't have any way to check that the array has the right type. In this case, I'm guaranteed that this is safe because this array is going to be initialized to all null, and therefore I don't have any bad things in that array to start off with. And the actual recommended practice is to ignore this warning using an annotation. This works just fine. Maybe it's not as pretty as we might like. This was fixed in later languages like C#, which didn't have so much legacy code, and they actually store the types at runtime, and so they can actually do this in a more elegant way. Another oddity caused by the late introduction of parametrics is the interplay between parametric and non-parametric types. Here I'm going to create an array list of strings, and then I'm going to create an alias to that array list, which is a plain type. And now, using the plain variable, I'll put something in. And note that this is perfectly fine for plain array lists, which are actually arrays of objects. So in old Java, we would have used subtype polymorphism to get this, We're just putting some object in here, the number 2 billion. No problems. But when we go to get this out, we are going to get an issue because we've gotten the number out, not a string, and we'll get an exception when that happens. Note that we get the exception on line 4, which is a bit odd because this line is playing by the rules. I mean, if you just look at line 1 and line 4 in isolation, what's the problem here? I've got an array of strings and I'm getting out a string. How can that be wrong? And yet I get the error there. This is a little sad. And it's because we're not carrying around types to actually check this put when it happens. It's interesting to note that Java does something different with arrays. Arrays were in the language from the get-go, and arrays do store their types at runtime. And therefore, Java can check arrays as they are assigned. So here, same code, but using directly arrays instead of an array list, we get the error on line 3, and the error is an array store exception. It says you're trying to put an integer into an array that is not an array of integers. This is an array of strings. That's possible because we dynamically know that the array is an array of strings. That's not possible here because there's no dynamic information about the parameter type on SS. Note that the parameter on the array inside the ArrayList class is no help to us because that was already erased too. So this is actually compiled to just be an object. There's no runtime information about this array at all, and there's nothing Java can do to stop the number from getting stuck into the array. Parametric polymorphism is found in almost every modern statically typed language. It was first developed for ML in the 1970s. ML has lots of modern descendants, including F# from Microsoft and the very popular OCaml programming language from INRIA in France. ML was originally a meta-language for a theorem prover, and there's strong connections between the language and mathematical logic. This has led to the development of full theorem-proving languages such as Agda and Coq. They're interesting to look at. The type systems in these languages are really, really strong. You can write things like a sorted list as a type. You can say it's a completely connected graph as a type. We're not normally used to thinking of those things as types, but they are logical specifications, and essentially what these languages do is use types to express any logically expressible formula. There's a related notation in C++, uses the angle brackets. You might have seen it. They're called templates in that world, and they look syntactically similar to Java, but they're very, very different. A template does not actually generate any executable code. C++ only generates executable code when the template is instantiated. So for example, if I instantiate a list of ints, I'll get one executable. If I instantiate a list of strings, I'll get another executable, another copy of that executable. This approach has some advantages because the compiler is run later on the code. It can specialize to particular classes that are passed in. In other words, the list doesn't have to work for everything. It just has to work for the things that it's given. That's different from what happens in Java, where when you write a parametric type, the parametric type must work for any type T. The disadvantage of C++ is that you get errors later because templates themselves aren't really compiled. You only compile them when you use them. And in addition, you have these copies of the executable code. With Java-style generics, you only have one executable for each class. So with C++, we don't have duplication in the source code, but we are going to have duplication in the executable, which will increase its size. In ML, we will not have this duplication in either place.